Welcome to our explainer. Today we're diving into a massive, glaring blind spot sitting right at the very core of modern artificial intelligence. You see, for decades, we've relied on classical information theory to understand how computers process data. But as AI models have exploded into these massive, incredibly capable systems, well, those old frameworks are really starting to show some major cracks. So, we're going to explore a groundbreaking new concept that actually, finally, explains what our AI models are really doing when they learn. Think about this for a second. Can we actually learn more from data than what existed in the process that generated it? This question points to a profound cognitive dissonance in modern AI. According to classical theory, specifically the data processing inequality, you just can't create new information out of nowhere, right? So if the computer is just following a basic, deterministic set of instructions, how on earth does an observing AI suddenly figure out highly complex emergent strategies that definitely aren't explicitly written in those original rules? Classical theory says you absolutely can't get more information out than what you put in. And yet, empirically, our AI systems are doing exactly that, literally every single day. So here is our roadmap for solving this mystery. First, we'll unpack the information paradox. Then, we'll introduce this new concept called epiplexity. After that, we'll compare entropy versus structure, explore emergence and computation, and finally, wrap up with the value of data.
Section 1. The Information Paradox.
Right here is where we find this intense tension between textbook theory and empirical reality. Classical theory basically presents three paradoxes that completely fail to explain modern AI. The thing is, standard metrics like Shannon entropy and Kolmogorov complexity, they really only measure unpredictability or raw compression. They completely miss the useful structure. First, the theory states that deterministic processes cannot increase information, yet we know for a fact that synthetic data improves model capabilities. Second, it claims information is independent of the order of the data. But come on, we know large language models learn so much better from English text when it's ordered left to right rather than scrambled or reversed. It clearly picks out an arrow of time. And third, classical theory says maximizing likelihood is really just matching a distribution. It assumes a model can't learn useful features that weren't explicitly used to generate the data in the first place. But our AI models, they are constantly uncovering vast amounts of hidden structure. Those classical metrics just come up completely empty-handed here. Just consider AlphaZero. This is a perfect example. It ingested absolutely zero human data, learning entirely from the basic deterministic rules of chess, which, by the way, you can write in just a few kilobytes of code. But the resulting model, it requires tens of millions of parameters to store all its knowledge. So if classical theory says no new information was created because the rules are deterministic, where did megabytes upon megabytes of deep chess strategy, tactical insight, and positional understanding actually come from? There's no way around it. The old theory is completely missing the mark.
Which brings us to Section 2. Introducing epiplexity.
To fill this huge void left by classical theories, we need a brand new metric, and it's called epiplexity. Basically, this is the formal measurement of structural information that a computationally bounded observer can extract from data. We are not talking about pure mathematical randomness anymore. We're talking about the useful, actually learnable patterns that an observer, like say a neural network with limited time and memory, can realistically figure out and store. In classical theory, we usually assume an unbounded observer. Think of it as having infinite compute. To this hypothetical godlike being, there's no mystery. It can instantly calculate all the basic rules, out to infinity, so it extracts zero new structural information because, well, it simply doesn't need to. But our neural networks? They are bounded. They have hard limits. They absolutely cannot calculate all possible chess moves to the end of time. And because they're bounded, they are literally forced to learn emergent shortcuts, things like protect your queen or control the center. This process of actively hunting for shortcuts is exactly what extracts massive amounts of structural information from the data. Now, take a look at this standard training loss curve. You see that flat dashed orange line sitting at the bottom? That represents time-bounded entropy. Basically, that's the unpredictable noise the model just cannot decode, no matter how hard it tries. But notice that green shaded area right above it? That gap right there, that is the epiplexity. It's the quantifiable, measurable amount of useful structural information the model actually had to absorb into its weights just to drop its loss down to that orange baseline. Moving on to Section 3, entropy versus structure. Here's a crucial point. Not all data is created equal. When we evaluate data sets, they actually fall on a spectrum that weighs random noise on one side against structural, learnable information on the other. For a bounded neural network, its ability to actually get smarter depends entirely on where its training data lands on this exact map.
Let's break this down. Take an API key. To a bounded observer, a secure API key is basically pure high-entropy noise. It's totally unpredictable, offering zero structural information, which means the model learns absolutely nothing from it. Now, on the completely opposite end, you have redundant computer code. It's highly predictable, but honestly, it's incredibly boring. It's low entropy, low structure. But animal images, now that is the sweet spot. With moderate entropy and high structure, the model is actually forced to build rich, complex internal circuits just to recognize fur, feathers, eyes, and shapes. This is what we call high epiplexity data. It quite literally forces the model to get smarter.
Let's dive into Section 4, Emergence and Computation. So, we've established that bounding compute forces a model to learn. To really test this idea, researchers used cellular automata, things like Conway's Game of Life. Now, if you're not familiar, these are just basic pixel-based grid rules, but when you run them step by step, they interact to create staggeringly complex, moving structures on the board. I know this looks a bit math-heavy, but let's translate this formal definition into an intuitive reality. Just notice the variables T1 and T2. These represent time bounds. If you ask a bounded neural network to predict the state of the game of life, say 100 steps into the future, it lacks the T2 compute to just brute force the math step by step. So to lower its loss within its much tighter T1 limits, it's basically forced to identify emergent concepts like species or those moving patterns we call gliders. It has to learn how they collide and interact. It constructs an entirely new, higher-level understanding of the system, purely to compensate for its lack of raw compute.
Let's bring this back to AlphaZero and compare it to a classic minimax chess algorithm. A minimax algorithm essentially assumes unbounded compute. It's a tiny, simple program that just brute forces future board states, meaning it contains zero learned structural information. AlphaZero, on the other hand, is heavily bounded in how many moves it can realistically search during a game. Because of this strict limit, it's forced to actually learn strategy. It builds millions of bits of epiplexity right into its neural network to intuitively evaluate the board. Think about that for a second. The limitation is literally what creates the intelligence.
Finally, Section 5, the value of data. So what does this all mean for how we approach AI? Well, as the researchers state, out-of-distribution generalization is fundamentally about how much reusable structure the model acquires, not how well it predicts in distribution. This is a massive, profound shift in thinking. Historically, we've focused heavily on standard training loss, basically how well the model memorizes its training data. But this research tells us that basic loss is just not enough. Two models can have the exact same loss, but totally different real-world capabilities. What actually matters is the reusable structure, the epiplexity that it built along the way. When the researchers tracked the epiplexity of datasets against out-of-distribution generalization, which just means how well a model performs on completely novel, unseen tasks, the correlation was undeniable. Datasets scoring higher in epiplexity force the model to learn much richer, highly reusable structural circuits, and those robust internal circuits directly translate to vastly superior downstream performance. It proves that you really should be selecting your training data not just to minimize loss, but to maximize the structural complexity the model is forced to absorb. It's a total game changer. Which leaves us with a pretty vital question. If a model's true intelligence really comes from the structural complexity it's forced to learn, how should we be curating the datasets of tomorrow? We can't just dump random data in our models anymore. We have to design structural curriculums, actively challenging our models to build the reusable architectures of intelligence. It is a completely new way to think about information. Thank you so much for joining me on this explainer, and I really hope it reshaped how you look at the future of AI training.